You see, gauge symmetry, that is the fact that the electric and magnetic fields do not change if we just change the vector potential by adding it a gradient of some function and the scalar potential by subtracting the derivative of the same potential. Neither E nor the B field, none of them change. Well, it lets you do some simplifications sometimes, but at some other times it can be a problem. So it gives you some freedom to simplify your life, but at the same time, for example, the questions whether phi is 0 or not doesn't really make any sense. Because phi can be 0 in one gauge, just making a gauge transformation, it will become non-zero in a different gauge. So in that case, if you want to ask questions like, is the scalar potential 0 in such and such a circumstance, you should tell me which gauge are you considering. Because without fixing one gauge, there is no answer to that question.
Peki hocam biz bu Lorentz gauge falan yazdığımızda ama transformation falan yazdığımızda hangi gauge yazdık? Lorentz gauge değil de.
Lorentz gauge, I mean, you see, phi and A need not satisfy that condition. But what we ask for is, we just look for the scalar and vector potentials that do satisfy that condition. That is what we mean by gauge condition. They don't have to satisfy that condition, but there are infinitely many scalar and vector potentials corresponding to an electric and magnetic field. So we add some additional conditions, not necessary by the Maxwell's equations, but we just, out of the blue, let's say, we add those conditions, hoping that out of these infinitely many scalar and vector potential pairs corresponding to the electric and magnetic field that we want to study, we just pick up one. If you impose some other condition, you will pick up some other one. So both are good enough to describe your electric and magnetic fields. But we had already seen that, for example, if you pick up the Coulomb gauge, the potential seems to be instantaneous. It seems to contradict with the fact that signals are transferred at a finite speed. But this is kind of the disadvantage of the Coulomb gauge. But the advantage is that, I mean, it's almost trivial to solve for the scalar potential. The expression for the scalar potential in that gauge is the same as the expression we had in electrostatics, the only difference being the charge density is now time dependent. So that's the only difference. Then we had the other gauge, the Lorentz gauge, which made it explicit that delay in signal transfer. But then the expressions just might be more complicated sometimes. So you just pick up a gauge condition that makes you happy and stick with it. The results should be independent of your gauge. Siz yer değiştirmişsiniz.
Peki hocam buna göre bu vektör field işte scalar potansiyeli sin cosine cinsinden bulabilir miyiz? Böyle bir şey çıkıyor.
Well, let's see. What does the Fourier series tell you? Or Fourier theorem tells you? Any function you can write as an integral over sines or cosines. Well, you don't need Maxwell's equations for that or electromagnetism for that.
Hocam bahsettiğimiz disadvantage aslında hani zamanla yok sayılan inisiyatifimiz diyor ya, o aslında mümkün kılınmaz yani o kullanmamız. Yani bunu belki bu yanlış bir kullanmıyoruz.
Not really. You see, things can travel at the speed of light. Objects, or not things, let's say. As long as there is no transfer of information faster than the speed of light. For example, we already looked at the case of electromagnetic waves in a waveguide. We had seen that their phase velocity is larger than c. In fact, in the homework you were supposed to prove, in the exam I think, that the phase velocity times the group velocity was c squared. So if one is larger than c, then the other one is definitely smaller than c. And in the explicit calculation, we showed that the phase velocity was larger than the speed of light. So what? There is no transfer of energy, no transfer of information, no signaling that goes faster than the speed of light. The signals or the energy moves with the group velocity, which is less than c. And the potential, okay, we invent this quantity called the potential, but it's not something that we can directly measure. What we can directly measure is the electric field. And even in that gauge, in the Coulomb gauge, the electric field takes a finite amount of time to move. You see, if you remember the expression of the electric field, which was minus the gradient of phi minus 1 over c del A by del T. What happens in the Coulomb gauge is, yes, the gradient of phi has some part which, where the information is transferred instantaneously, it seems. The signal goes instantaneously from one point to the other one in this part, but that part is exactly canceled by this part because A also has a part that changes instantaneously. So these two cancel each other, and electric field always moves less. The changes in the electric field always move less than in vacuum at the speed of light c. So since it's the electric field that is measurable, for which the signals are moving less than the speed at the speed of light, not faster than the speed of light, so I don't care whether phi moves, where the deformations in phi move faster than the speed of light, because that is not something I can really measure. Just like the phase velocity in the electromagnetic waves in guides. In waveguide, what I care about is the transfer of energy. That is at a speed less than the speed of light. Of course, you might not like the idea, even for the potential, that it moves fast, that the changes move faster than the speed of light instantaneously. Okay, then fine, don't use the Coulomb gauge. But there's no physical justification for that choice. It's just your preference. Your friend might prefer to use it. Other questions?
Hocam, bu en son yazdığınız şeyde dedik yani, parçacık kendisine kuvvet uyguluyor. Ve o durumu o parçacık olarak nasıl duruyor ki? Yani, Newton'un force'la denk geldiğini kendisi etmiyor diye düşünüyorsun.
Okay, so
Parçalaması gerekmiyor yani. Parçacık bir şey dağılıyor.
why should it just be destroyed?
Yani dışarıdan hiç external force uygulamıyor mesela. Ama Newton'un force'u yine var.
Okay.
Kendisine kuvvet uyguluyor o zaman.
Yeah, you see, if you go to empty space, or if you like watching space movies, sometimes people just end up in empty space and they explode. Have you seen such a movie? No? Well, if you go to empty space, there's some internal force you have. There's the pressure of your blood, of your cell, internal pressure of the blood, of the cells, etc. But they are not strong enough to cause an explosion. If you find yourself in vacuum, well, you won't last long, but you definitely do not explode. So why should a particle exerting a force on itself should explode?
Ama bizim mesela vakıfta olsa bu yüzey gerilimi desek işte yani internal force'ları cancel edebilir.
Okay.
Tatlamayabiliriz ama parçacığın üstünde de mi yüzey gerilimi var?
Well, it's a point particle to start with. It's not one part exerting a force on the other part. So there are no two parts of your particle anyway. There was this model in the book where he describes that force as these two parts somehow that stick together, that they have other internal forces, not necessarily electromagnetic, hypothetical forces, let's say, that keeps that intact. And due to the retarded forces, the book claims that they will exert forces on each other if they are accelerating. And the book describes that as the origin of the internal force of that force that we found. But that force is already problematic. I mean, because of other reasons. Because you see, in mechanics, most of the time we said that, okay, the particle cannot exert a force on itself because otherwise it would just accelerate on its own without any external forces, which doesn't make sense. I'm sure you remember such arguments from mechanics. But you see, this particle we had, if there are no external forces acting on this particle, the acceleration of this particle is just had this form. It accelerates on its own. So this is kind of a problem. At least some people claim that this is basically an indication that the point particle doesn't make sense. So some calculations suggest that all these problems, they disappear if you take a finite-sized object. But you see, we don't have a consistent framework to describe these systems yet. It just tells us that at least in electrodynamics, whether in classical electrodynamics or even in the quantum version, point particles have their problems. We can manage to sweep them under the rug, but we don't really have a fully consistent answer. I mean, if we try to, let's say, add gravity to this, you see, an object of a finite mass that has the size of a point is what we call a black hole. So there we again see some problems in this concept of point particle. All point particles should be black holes if you add gravity to it. But that also doesn't make sense, because we also know that the black holes, they do not differ from each other. The only information the black holes can have, as far as we know, as far as the Einstein theory of general relativity tells us that, is that they can have angular momentum, they can have charges, they can have mass. That's it. They can have no other property. But that tells me that, for example, then a point like electron should be the same thing as a point like muon, which we know that is not the case. So this is just an indication that we still have problems when we have point particles.
Should rigid body model also fail because we consider that as a set of collection of point particles?
Well, you see, the rigid body, yes, we do consider. We start by considering them as a set of very small particles, then take the limit as point particles. But those points have zero charge, zero mass, zero size. Everything is zero. So everything kind of cancels. All these inconsistencies cancel. But rigid body has its own problem, especially accelerating rigid bodies, according to relativity, because by definition, rigid body doesn't change its shape. But if you have your rigid body, if you just exert a force on one side, or one point on your rigid body, well, that information, that change in acceleration should take a finite amount of time to reach the other end. In this finite amount of time, this point will move a distance different than the other points. That means the object will be deformed if it's accelerated. But that means it's not a rigid body. So in relativity, we cannot even have rigid bodies. Anyway, let's go back to our course of electrodynamics without this problem. Any other questions? Now, basically, we will be changing subjects. That's why if you have any questions left in your mind, it's time to ask. Yes?
The relationship between phase velocity and group velocity, is it only valid in vacuum or in dielectric medium?
That's in waveguides. Well, in fact, that is basically because of the fact that omega squared is equal to k squared plus some constant. As long as that relation holds, the phase velocity times the group velocity is equal to c squared. In waveguides, we have such a relation. Other questions?
Hocam envelope elde etmek için waveguide'a mı ihtiyacımız var yoksa vakumda da envelope oluşur?
Come here. Hold it. Yes. This is the envelope that you see. It's not a harmonic wave. So it's just some general shape moving with some velocity. That's what we mean by an envelope.
Bir tane dalga var.
You see, a harmonic wave, single harmonic wave, should be infinite in size. That's how we define the harmonic wave, and it should be infinite in time also. Anything that is not infinite in size and infinite in time should have a non-trivial wave envelope. Okay, so let's start with relativity. Now, what do you remember about relativity?
Lorentz transformations.
What else do you remember about relativity? Time dilation. Length contraction. Two postulates.
Timeline.
Well, let's see, these are not relativity, these are special theory of relativity. The idea of relativity goes much before Einstein. So before we had Galilean relativity, so basically the concept of relativity in a narrow sense, let's say, it just states that the laws of nature should be the same for every observer. So this is one of the postulates. Well, to this, Einstein adds the second one. The speed of light is the same for every observer. All the rest can be derived from these two, let's say, postulates. Well, let me just make one correction. If you remove that inertial, it becomes general theory of relativity. Now, let's first look at the Galilean transformations of relativity, Galilean relativity. Let's just consider two observers or two different reference frames. At t equal to 0, both reference frames are at the same point. So this is one reference frame, xy. This is the other one, x prime, y prime. This is at t equal to 0. Then let's say that this red reference frame is moving relative to the black reference frame with some velocity, with some speed, let's say v in the positive x direction. At the time t, the black reference frame is over here. The red one is over here. Let us assume that they are both looking at an object. That started over there. And let's reduce the problem to one dimension. It's also moving relative to the black reference frame, V0. So what this means is that if initially it is at this point, x0, after a time t, it will be at this point, x1, no. x1. So according to the reference frame of the first object, of the black reference frame, delta x is just x1 minus x0. So delta x over delta t is x1 minus x0 over delta t, which is v0. Now let's look at the second reference frame, the red one. According to the red one, initially it's at the point x0. And then it is, let's say, this distance is x1 bar. And then finally it's that x1 bar divided by delta t. Now, this is the change in its position. So its velocity, let me put it v bar, is x0 minus x1 bar divided by delta t. Now this distance over here, let's call it d. You would say that, okay, d plus x1 bar is equal to x1. So x1 bar is equal to x1 minus d. So the v bar, the velocity measured in the red reference frame, is equal to x0 minus x1 plus d over delta t, or x0 minus x1 divided by delta t plus d over delta t, which is equal to v0 plus v. This is v0 bar, sorry. Do you agree? Well, let's say v0 bar is the speed relative to the red reference frame. If v is equal to v0, so the red reference frame is moving with the same speed as my object, its speed in the red reference frame should be 0. But it is definitely not the case. So where did I make a mistake? Okay, that my first mistake. x1 bar is x1 minus d. You see, x1 bar is the x coordinate in the red reference frame. D is the distance that the red reference frame covers from the initial point. So x1, which is this distance, it started from x0 and then ended up at x1. So this distance, which is x1, should be x1 bar plus d. So v0 bar is x1 minus x0. Now here, x1 minus x0. Because the velocity is defined, speed is defined as the final position minus the initial position. So this is minus plus, minus plus, minus. x1 minus x0 minus, okay, minus. Of course, this contradicts with the second postulate. You see, the second postulate says that the speed of light is always the same for every observer. If this blue object is light, it has different speeds for different observers. If this law were correct. So what is wrong in this law, in this derivation now? What assumption did we make, which is not in general, not really true? Hmm? Okay, that is one mistake we made. Basically, we have two mistakes. You see, what is D? Who measures D? So it's the black reference frame that is measuring D. That is measuring the speed of the red reference frame. But here, we are kind of assuming that when we are writing this one, basically, we are assuming that B measured by both of those are the same. So that's the other assumption that we are basically making. So those two assumptions leads us to this Galilean relativity of speeds. Now we should correct them. And if these two assumptions, that the time is the same and the speed of and the distances are the same, hold, so inevitably we have the Galilean relativity, and the speed of light will be different for different observers. In fact, for many years, people looked for an explanation in which the speed of light didn't have the same velocity for observers, for every observer, but basically it failed. So it was this concept of the ether. One of the problems is in our electromagnetic phenomena, okay, first of all, we have the reference to velocity. Everything is velocity dependent. But velocity changes from reference frame to reference frame because of Galilean relativity, and also because of Einstein's relativity. But at the same time, the speed of light is c. We just derived it. So in which reference frame? So there was the claim that without really being aware of, we are assuming a particular reference frame in which this so-called ether is at rest. So the speed should be measured relative to ether. All the speeds should be measured relative to ether. So Maxwell's equations are valid in the reference frame in which the ether is at rest. So that was, for quite some time, people tried to look for it. But the problem was then Earth is moving around. If Earth is moving around, it's not moving at constant velocity, its speed relative to ether will be changing from time to time. So the agreement with observation and Maxwell's equations should be changing from time to time, depending on the velocity of the speed of Earth relative to ether, which was not observed. And eventually it was so people speculated that, okay, maybe it's not the Earth is dragging the ether along with it, so Earth is locally always at rest with respect to ether. No matter in which direction it's moving. It's like you hold this object, if this is the ether, you hold it, and you just move around with it, so this object is at rest with you all the time. So this was kind of one of the attempts to explain the non-observation of the expected discrepancy, but then the theory became more complicated, and eventually we had the Michelson-Morley, after the Michelson-Morley experiment, the conclusion was that even if there is ether, we cannot observe it. So we cannot observe the motion of any object relative to ether. Well, we didn't prove that it doesn't exist. We basically proved that we cannot observe it.
Peki şimdi bu hani dark matter falan deniyor ya, o acaba eterlerine geçebilir mi?
Well, you see, we have many other concepts now, not just the dark matter, but many other things that, for me, if you ask my opinion, we have just renamed ether. We have many ether concepts. But we are not calling it ether because of the bad reputation it has. We are calling it vacuum. Well, anyway, it's still non-observable because of the length contraction and time dilation. Any measurement that you make, you will not be able to observe it. Now, you see, if you look at the two postulates, well, they look quite innocent. I mean, they shouldn't have significant consequences. But one thing is, one shocking consequence of those two things is that the simultaneity. So this is a frame-dependent quantity. It might be that an observer sees two events as simultaneous, in his reference frames it will be simultaneous, in a different reference frame it will not be simultaneous. A typical example of this one is you have your train. There is a, let's say, a light bulb in the center. If you turn on the switch, t equal to 0. For an observer on the train, light reaches, let's say this is point A, this is point B. Points A and B simultaneously. Well, of course, it's not so trivial to say whether light reaches simultaneously or not. You see, you also need to make an observation. So one thing you can devise is just put some electronic devices over there that will signal the arrival of light. And then you can connect those by a wire to a device, let's say, somewhere in the train, preferably in the center. But of course, you also need to make sure that, well, you see, the signal that whether that light has arrived or not will also take some time to reach your device eventually, if you want to compare the time difference between the arrival of light to point A and point B. So one possible realization of measuring that will be just obtain identical devices, having identical lengths of wire, etc., so that the signal will take the same amount of time to go from one end to the other end. So put one of those detectors over here, the other one over here, bring the wires to the center. I mean, as long as the length of the wires are the same, you can just put them anywhere. So and at the end, just measure the difference between those two signals that arrived at your point. That is one way to make sure whether they arrive at the same time or one arrives first and the other one arrives second. Or you might be just put some sensors over there. When there is some light reaches at those sensors, they might just turn on another light, a second light. You might just stay somewhere over here inside the train and just look at those two lights, those secondary lights that are triggered by your sensors, and measure when they arrive at your position. But then, of course, you have to take into account the fact that if you are not at the center, light will take a different time to reach you if it's from the B or from the A. Then you have to make corrections accordingly. And if you make such corrections accordingly, the observer in the train will conclude that the light reaches A and B at the same time. Again, as I repeat, it's not so straightforward to say whether light reaches, to make an actual measurement which says that the light reaches A and B at the same time because of the delays that will inevitably be there because light travels at a finite speed. You have to make corrections due to those delays. So for this observer, after all those corrections are made, event A and event B, that is the light reaching the point A and the light reaching the point B, they occur at the same time. Now, for an observer at rest in the station, take the same system. course, now it will be moving with some velocity v relative to the station. Now, if, let's say, at the time t equal to 0, the light bulb starts emitting light, it will take a finite amount of time for the light to reach the point A and point B. In that amount of time, the train will move some distance. Now, this is the new position of the train. So the observer on the station will conclude that light reaches point A. Before reaching point B. So one observer says that they are simultaneous. The other observer says that they are not simultaneous. And as I said, this is not due to the finite amount of time the signal takes to reach the observer. After we correct all those delays until the signal reaches the observer, what remains is this.
So if the train moves, if the train moves with the speed of light toward the right direction, the light never reach B.
Well, you see, the questions starting with if the train starts moving with the speed of light doesn't make sense. It doesn't exist.
No, I mean theoretically.
Even theoretically, they do not exist. So you can end up having all these paradoxical conclusions when you start with saying if the light starts with traveling at the speed of light c. Because according to the observer on the train, it will reach there in a very short amount of time. You see, if any object moves at the speed, anything moves at the speed of light c, it moves with the speed of light c with respect to any observer. So then it just doesn't make sense to talk about the observer on the train also. It just cannot exist.
No, I mean, for example, the light comes with the speed of light and the train and the point B is also moving with the speed of light and light cannot reach it if it happens at the same time.
So what do you mean by point B moving at the speed of light c? Which observer are we talking about also?
About the observer in the station.
Observing, okay, it will never reach that point B. So what?
So the observer in the station will see the point B dark, but the observer inside the train will see it light.
You see, the inside the train, what do you mean by inside the train? Is it the point B is inside the train, so you cannot have an observer on the train. Because you see, for an observer on the train is at rest. If an object is moving at the speed of light c, it is moving at the speed of light c for every observer. So you cannot have an observer that is at rest relative to the point B. So that's why I'm saying that if you start with saying that if we have a train that is moving at the speed of light c, no, you cannot have it. If you are saying, okay, there is this mathematical point moving at the speed of light c, but then there's no train, so there's no observer on the train.
O zaman hocam, fotona göre fotonun hızı sıfır.
Photon is not an observer. It's not a reference frame. So there is no reference frame in which the photon is at rest.
Üstüne observer koyamam.
No. No reference frame moves at the speed c. So once you accept that fact, the sooner the better. most of your questions will be automatically answered. Another cause of confusion is this simultaneity. For example, there is this so-called paradox in which, so you have, let's say, a container which has some finite size, and you want to put an object inside the container longer than this container. So if you move this object speed close to the speed of light, it will contract. So we will study contraction, Lorentz contraction. It will contract, but if it contracts, it will be able to fit inside the container. But according to an observer on the object, the container will get shorter. So it won't be able to fit inside the container. So let's say this is the problem. Let's just imagine you have a garage, and there is a car. And the car has a length, let's say, L, and your garage has a length L prime, which is less than L. So if the car is moving fast, close to the speed of light, so it will Lorentz contract, it will get shorter, but if it gets shorter, it can fit in the garage. On the other hand, for an observer on the car, the garage is moving very fast, so it will be Lorentz contracted. So according to him, it should not fit in the garage. So how come? Well, the answer is in the simultaneity. What do you mean by fitting in the garage? To be fit in the garage, as your friend points out, means that both this point, both the front point and the back point of the car should be within this length of the garage simultaneously. But as we had seen in this example, simultaneity is a frame-dependent quantity. So when these two observers, one is in the garage, the other one in the car, one says that, okay, the car will not fit in the garage, the other says that it will fit in the garage. They are both correct because basically they are talking about two different things. Because they have different meaning for simultaneity. They are both correct. And there's no paradox with that. They are correct at the same time, simultaneously. This is not frame dependent. Any questions before the break? Yeah, after the break, we can just derive these laws of Lorentz contraction and time dilation.
What about twins paradox?
There's no paradox there. Again, the problem is, you see, one of the twins, you see, I'm sure you are all familiar with the twin paradox. You see, we have these twins, one takes a space shuttle and moves to the next star with a speed close to the speed of light. He goes and comes back, and when you compare the two twins, the twin that moved is younger. So if you just look at the two observers, the observer on Earth sees the other twin, he will slow down. So to say, his biological clock will also slow down. So when he comes back, he will look younger, so there's no problem with that. But if you look at the perspective of the twin that took the shuttle, he will see the other twin on Earth moving at speeds close to the speed of light. So according to him, he should stay younger. Well, when you bring both of them together, well, it's either one or the other one that is younger. You cannot have both of them. So which one is true? Where is the paradox? The paradox doesn't really exist because let's look at the postulates. Inertial observers. The twin that went to the next star and came back is not an inertial observer. It's accelerating all the time. So you cannot take the perspective of the twin taking the shuttle. The observer on Earth is the correct one. The other one, he will get older than his twin that took the shuttle. Well, if you remove that inertial constraint, then you are in the realm of general relativity. General relativity also agrees with it. You see, the problem is, according to the twin on the shuttle, he is constantly in a region where there is some gravitational field. And gravitational field slows time down. So he will stay younger than his twin on Earth, according to his observation also. So there's no paradox. Anyway, we will discuss them after the break.
Is it happening experimentally? This project, its own set is going to